The topic of this report is the electrochemical preparation and properties of aluminum-zirconium alloys. Today, the most common method for the synthesis of aluminum-zirconium alloys is the direct mixing of molten metals. This method, while simple to implement, has a number of significant drawbacks, including high process temperature, the need to use pure starting metals, and significant irretrievable losses of both zirconium and aluminum due to oxidation. The second method for the synthesis of aluminum-zirconium alloys is based on aluminothermic reduction of sodium or potassium fluorozirconates in a salt flux layer. This method has a high intensity of the process and a high degree of extraction of zirconium into the alloy. However, it requires a large consumption of expensive salts, which increases the cost of the resulting alloys. The method we are developing is based on aluminothermic reduction of zirconium dioxide in the environment of molten fluoride salts, which makes it possible to use cheaper oxide as the main component and, as a result, reduce the cost of the resulting ligature. All experiments are carried out in air without using an inert atmosphere. The experimental cell is a graphite crucible, number 1, placed in a protective crucible of aluminum oxide number 4. To prevent burning of the main crucible, the space between the crucibles is filled with graphite powder 2. The molten aluminum located at the bottom, which is simultaneously the cathode, number 5, is mixed with a graphite stirrer number 8, which is also a current conductor, and as the anode using graphite plate number 9. The temperature of the molten flux number 3 is controlled using a thermocouple number 7. For an additional load of zirconium oxide, use a quartz tube number 6. In order to evaluate the efficiency of extracting zirconium into the alloy, all the samples obtained were studied by a chemical method using an optical emission spectrometer. The structure and distribution of zirconium in the alloy were studied by scanning electron microscopy using a scanning electron microscope, and the phase composition was studied using a diffractometer. The microphotographs of the alloy show that at high zirconium contents in the alloy, most of it passes into intermetallic compounds, the sizes of which can vary from 5 to 50 microns. It was also found that cracks are observed in the structure of intermetallic compounds larger than 50 microns in size, which will contribute to their dissolution upon melting. According to the results of the X-ray phase analysis, the obtained intermetallic compounds have the composition of aluminum-3 zirconium. It was also found that the microhardness of the alloy in areas free of intermetallic compounds increases with increasing zirconium content, while the microhardness of the intermetallic compounds themselves can reach 100 Vickers units. When studying the corrosion resistance of the alloy, it was found that the most intensive dissolution of the base metal occurs at the metal intermetallic compound interface, which is clearly seen in Figure C. From this we can conclude that intermetallic compounds are cathode sites with respect to the main alloy. It has also been established that corrosion proceeds with oxygen depolarization, and a structural alloy containing 0.4 mass% of zirconium is less susceptible to corrosion damage than the rest, which may be associated with fewer intermetallic compounds and, as a consequence, a more uniform structure. Conclusion. It is established that the main part of zirconium in the alloys is represented as intermetallic compounds with a zirconium content of 52 to 53%, which corresponds to a compound of the composition aluminum-3 zirconium. With an increase in the zirconium content in the alloy, the microhardness in the areas free of intermetallic compounds increases from 15 to 36 units according to Vickers, while the microhardness of the intermetallic compounds itself can reach 100 units. It was established that the aluminum-zirconium 0.4 alloy obtained by electrolysis of the fluoride melt has an increased hardness and corrosion resistance in comparison with pure aluminum. Thanks for your attention.